This problem says a frog makes 4 jumps in a row. The displacement vectors for the 4 jumps are 30 centimeters due west, 20 centimeters 38 degrees south of west, 25.5 centimeters 46 degrees south of east, and 33 centimeters 35 degrees north of east. We want to find the magnitude and direction of the frog's total displacement from its starting point. Express the direction as an angle measured counterclockwise from due east. Now I've come up with a sketch of this frog's path of motion that I created with 4 displacement vectors, which could be labeled as delta R1, delta R2, delta R3, and delta R4. In the end, what we have is what would be called delta R total. So the idea that's being used here is we want to find the delta R total, the total displacement for the frog, by summing up all of the individual displacements from I equals 1 to 4. In other words, we need to do delta R1 plus delta R2 plus delta R3 and plus delta R4. We have to do vector addition on all these. Now first of all, notice how I drew the vectors. The first one was 30 centimeters due west. So this is going to be a magnitude of 30, and it points directly to the left, which is the negative x direction. That's the west direction. This is north, east, and south. Our next vector is 20 centimeters, 38 degrees south of west. So this is going to be a 20. And when I measure the 38 degree angle, it has to be south of west. So we start from the west direction, and then we rotate 38 degrees toward the south direction. We need 25.5 centimeters for this one. And this has to be 46 degrees south of east. So think about going east first of all, and then rotate 46 degrees south of that. This one says we're going to go 33 centimeters at an angle of 35 degrees north of east. So I started off thinking about the east direction, and then I just rotated the angle 35 degrees from there. And I figured that that put me right about here for a final location of the frog, and we need to figure out how far he is away from his initial starting point, and also what angle is he at relative to his initial starting point. When we finally get that standard position angle, we're going to want to measure it counterclockwise from the positive x direction, so it'll be an angle that's greater than 180, but less than 270. Alright, so that's the setup of the problem. Hopefully we all understand the problem now. And what I'm going to do is I'm going to find the components of each displacement. Because when we add vectors, we have to add the x components together separately from the y components. The x components get added together, and the y components, they get added together too. Alright, so what I'm going to do here is I'm going to just write down a few givens, namely that the delta R1 is 30 centimeters, delta R2 is 20 centimeters. These are the magnitudes or lengths of the displacements. And I'm going to use these in my calculations. Okay, so let's make ourselves a table. This is the magnitude. We're also going to want to find the theta in standard position. So theta 1, that would be the angle of displacement vector r1. Now this vector points directly in the negative x direction. So how much rotation has there been from the positive x direction? Well, if you measure it counterclockwise from the positive x direction, you can see that it goes halfway around the circle. That's an 180 degree standard position angle. So let's put that in. Now let's find the standard position angle of delta R2. Now we have a reference angle here of 38 degrees with the x-axis, but we have to go farther than that. We have to measure our angle from the positive x direction, so we have to do this. So what will the standard position angle really be for that direction? It's more than 180. It's 180 plus 38. That's going to be 218 degrees. Okay, now let's find the angle R3 in standard position. Here's a little reference that I drew which shows the positive x direction. So let's start here and go all the way around. It's more than 270 degrees. We can use 360 minus 46. That's 314 degrees. And finally, this vector, it points toward the first quadrant. So its reference angle actually is the standard position angle. So theta 4 is 35 degrees. Let's just check to make sure that the angles we got make sense. So delta R1 points to the left. That's 180 degrees. That's correct. Our delta R2 points to the third quadrant, and we have an angle between 180 and 270, so that's good. Delta R3 points toward the fourth quadrant. We should have an angle between 270 and 360, which we do. Our delta R4 points toward the first quadrant, and our angle is between 0 and 90, so it all looks good. Next, we're going to want to find the x component and the y component for each. Now the formulas that we'll use for this will be delta r times the cosine of theta standard for the x component, and then we'll use delta r times the sine of theta standard for our y component. So 30 cosine 180 gives us negative 30 centimeters. 20 times the cosine of 218 gives us negative 15.76 centimeters. 25.5 times cosine 314 will give us 17.71 centimeters. And 33 cosine 35 gives us 27.03. Okay, great. Do these numbers make sense? Yeah, our first vector is going to the left, so we should have a negative x component. Our next vector is going to the left, so that x component should be negative. The next two vectors point to the right, so they should have positive x components. Now let's do the y components. We'll use 30 sine 180. It's going to be 0. 20 sine 218 gives us negative 12.31. 25.5 sine of 314 gives us negative 18.34. And 33 sine 35 gives us 18.93. All right, now what we'd like to do is find the sum of these components. So our sum of delta x will be negative 1.02 centimeters. And then our sum of delta y is negative 11.72. So these are going to be the horizontal and vertical components of that final resultant vector. All right, so we should be able to now say what our final R total is going to be. It's going to be negative 1.02 centimeters, comma, negative 11.72 centimeters. That's component form. Great. We're also asked for the magnitude now. To get the magnitude, we want to use the square root formula, where we take the square root of the delta x squared plus the delta y squared. Okay, this is delta R total. Now here I have a vector over its head. Here I don't. If we don't have a vector over its head, then it's assumed that this could refer to the magnitude or just the size of it. So let's plug in. I get 11.76 centimeters. This is the magnitude of the displacement. All right, we're also asked for the angle of the displacement in standard position. So for that, we'll first use the reference angle formula. Take the tan inverse of your delta y over your delta x. It's approximately 85.0 degrees. And we can see from our components that we're actually pointing in the third quadrant, because the delta x is negative and the delta y is negative. We can also see it in the picture here. So our standard position angle then will be 180 plus 85, which is 265 degrees.